Okay, so today we're going to be doing 7.4, which is going to be graphing rational functions. And just to mention that you want to make sure you have some kind of graphing software available. If you have a computer, you can use Desmos on that. A phone, you can use Desmos, or you can use a graphing calculator. Those are really the options that will work here. And we're going to be graphing rational functions. So let's talk about some important key features of rational functions that we need to recognize and some vocabulary. So if we zoom in here, rational functions are going to be basically a polynomial divided by another polynomial expression equal to f of x or y. And two things that you need to be able to identify is the leading coefficient. So the leading coefficient is the coefficient of the highest exponential term, okay? And then you're also going to need to identify the degree of the numerator. So that's going to be the exponent that's on the numerator. And then the same for the denominator. The leading coefficient of the denominator is known as the letter b. So we use the letters a and b to denote that. And then the degree of the denominator, you're also going to need to, when I say those things, you're going to need to know what I'm talking about. So that's some important vocabulary. And then we're going to talk about discontinuity. So does anybody know what discontinuity looks like on a graph? No? It's the opposite of a continuous graph, meaning that the graph basically breaks off at a certain section. Okay, it doesn't actually continue at that point. So that's what we call discontinuity. And there are two types of discontinuity. There's what we call holes in the graph, which basically look like open circles. And then we also have vertical asymptotes. And vertical asymptotes are the type of asymptotes that can never be crossed. Horizontal and slant asymptotes can sometimes be crossed. So let's go ahead and look at some of the key important features of what we need to know to do this. So, horizontal asymptote. You're going to start by identifying the degree of the numerator and denominator of your polynomial. There's three different types that can occur. There's a top-heavy situation, basically degree, which means that the degree on the top is larger than the degree on the bottom. And there are some cases where this results in what we call a slant asymptote, and we'll do an example that has one of those today. We also have what we call a bottom-heavy degree, which means that the degree on the bottom is larger than the degree on the top, and that always results in a horizontal asymptote of y equals 0. And then we have a situation where the degree is the same, and that means that the line a divided by b is the horizontal asymptote. So that's basically the quotient of the two coefficients. And then you're going to need to factor your polynomial and then find its discontinuity as well as its intercepts. So this is going to be like kind of like your little key, like your important, this is going to be important for like a quiz or anything like that. You're going to want to use this as a resource, okay? So this is kind of like your little instructions manual, okay? So let's go ahead and look at an example together to start. So I'm going to make this a little bigger because I noticed it was a little tiny. I don't know why. So let's make it a little bigger. So the first thing we're going to look at is the degree. So let me zoom in for a little bit. We'll look at the degree here. So what is the degree of the numerator? What's the exponent on the x? 1. Everybody see where the 1 came from? Make sure you guys are with me because this topic is tricky if you're not paying attention. It's very difficult if you're... Alright, so then the bottom. What's the degree of the x in this one, the bottom? 1. So that's the exponent on the x. So now you're going to determine, are these degrees the same? Is the top one bigger or this bottom one's bigger? These are what we call same degree. So since the degrees are the same, we follow the same degree procedures on your instructions manual on the top there. So if the degrees are the same, that means that the line y equals a divided by b is the horizontal asymptote. So I'm just following the instructions on that page there. Y equals a over b is going to be my horizontal asymptote. Let's talk about what a and b are. A and b are just the coefficients of your highest degree term, okay? So What is the coefficient of the x in the numerator? Good. And what's the coefficient of the x in the denominator? Right here. Also 1. So that's going to be y equals 1. So if it had a number in front like 2x or 3x or 4x, that would have been the coefficient. So if you don't have a coefficient, it's an implied 1. So this is your horizontal asymptote, okay? So if you want to go ahead and graph your horizontal asymptote, you can do that now, or you can wait until the end. I'll do it at the end so I don't have to zoom out quite yet. The next thing you want to determine is make sure that this polynomial expression, that it's equal to y, basically the function, is fully factored. So is there any further factoring that we need to do? No. There's nothing else to factor, so we just leave it as is. If it needs to be factored, you need to factor it at this stage, okay? So sometimes they will need to be factored. And then we're going to move on to discontinuity. There are two types of discontinuity, removable and non-removable. As for removable, the way we identify the removable discontinuity is we see if anything in this equation is going to cancel out. Is anything here going to cancel out? No. So there are no holes, which we call the no holes, and that's because nothing cancels out. So there are no holes because nothing cancels out. If something did cancel out, we would have a hole, and we'll talk about how we find that, when that comes up. And now we're going to go into non-removable. So non-removable, these are what we would call our vertical asymptotes, okay? Non-removable discontinuity are vertical asymptotes. And how you find these is you take the denominator, if there is one, and set that equal to 0. So is there a denominator in this function? Yes. So you're going to take the denominator and set it equal to 0. And that's going to give me x equals -2. And if there were multiple products in the denominator, you need to set each one of them equal to 0, okay? This one just happened to only have one to set equal. So we have our vertical asymptote, we have our horizontal asymptote. Let's move on to the next one. So the next thing we are going to look at is going to be x-intercepts. So the way you find x-intercepts in this type of problem is you take the numerator, any of the factors in the numerator, and you set each of those numerator factors individually equal to 0. In this case, there is only one numerator factor, x plus 4, or was it was x minus 4, right? Yeah, x minus 4, not x plus 4. And then you would solve this by just, solving for x. And this gives me x equals 4, which means my x-intercept is 4, 0, and we only have one of them here. So set the numerator products equal to 0 to find the x-intercepts. Now we're going to find our y-intercepts. And the way we find our y-intercepts is you take the entire equation, okay, and you replace all of the x's with 0, and then solve for y. So I just take my entire equation, I replace the x's with 0, and I solve for y. And that comes out to be -2, which means my y-intercept is 0, -2. Just like that. So now we have a good amount of information about our graph. So let's zoom out so we can graph it. We wait until the end to identify 6, 7, and 8 because those are graph dependent, meaning we require the graph to do that. Now, this particular question is actually pretty straightforward. You probably could hand graph it, but I'm going to teach you how to do it on Desmos. Before we do any of that, we need to graph the pieces of information we just came up with. So let's go ahead and graph our asymptotes first. We have a horizontal asymptote at y equals 1. Now keep in mind that horizontal asymptotes are not absolute, as in the graph can sometimes cross these, but they usually help us determine end behavior. But vertical asymptotes, however, can never be crossed. So just keep that in mind when we're doing these problems. I just want to address the differences there. And then we have a vertical asymptote at, which if I could draw it properly, would be at -2, like this. Alright, and now we're going to graph our x-intercepts. We only have one because there was only one factor in our numerator, so we're going to plot that at 4, 0. And then we have one y-intercept, which you only will have one typically, and that will be at -2. And that's what we have about our graph so far, which isn't a lot of information, because basically we need to, finish finding points on the graph. Now you could plug points in and get outputs, but why do that when the software can do it for you? So I have Desmos pulled up here. I'll try to make it small for now so that you can see what I'm typing in. So what you're going to do here is you're going to pull up Desmos and you're going to type in y equals. Now with your numerator, you're typically going to have to put it into parentheses, because otherwise when you try to divide, it's going to only divide one of the terms over x plus 2. And as you can see, it's going to graph our equation. Okay, so test it out. Make sure you feel comfortable with plugging that into Desmos. Once you plug that into Desmos, it's not a bad idea to also graph the asymptotes as well. It kind of helps you see visually what's happening with those asymptotes. So y equals 1, and our other asymptote was x equals -2. So as you can see, I graphed both of my asymptotes and my equation, and you can get a general look at what it looks like right here. Okay, so this is what the graph looks like. Was everybody able to do that? So now what I would like you to do if you're on Desmos is there's this little button that looks like a gear and it says edit list. Click on that button, and when you click on that button, it's going to give you an option to convert to a table on the first equation here. If you click on this option, this gives you a table of values, basically a t-chart, a table, which tells you the inputs and outputs of your function. Yes?
That works on every single graph.
Yes, the only time it's not going to work is when you have x equals a number, because technically that's undefined, a vertical line. However, you don't need to know that, the table, because that's a more obvious graph than the one right here.
That's going to save you so much time.
Right? It's so much easier. I know. So this basically just tells you the inputs and outputs, so you don't have to plug in each individual value and calculate it. It does the math for you. So you can type in any value you want to find too. Like I can type in a 3, I can type in 4. It will tell me whatever point I want to know. So when I'm taking values to plot on my graph, I'm taking those directly from my Desmos table. So if you're wondering where I'm coming up with these are just from the Desmos table. Okay? So we want to get enough points that will give us a general look at what our graph looks like. So doing that, they tell me that 4, 0 is a point, which we actually already knew. They also tell us that -1, -5 is a point. That's helpful. They tell us that -1 is a point. So now we have a pretty good look at this side of the graph right here. So we can graph that portion. But remember, if you saw the graph on Desmos, you saw that it actually had like a duplicate of that graph, right, on this side over here. Everybody see that? So I also am going to need to find some points over here to figure out what that side of the graph is going to look like. So what I can do here is start typing in values on this side of the axis. So -5, for example, gives me 3, so -5, 3. So 1, 2, 3. And maybe we can try a -4, see what that gives me. -4, 4. And we'll try a -3 as well, which gives me 7. And then we'll do -6, which gives me 2.5. That's not too bad to graph. 1, 2, 2.5. So that's what this side of the graph looks like. So does everybody feel comfortable using the table option on Desmos now? How it works? Okay. So this is what your graph is going to look like using the Desmos table. You have a question? No. Okay. So now we're going to look at our domain and range. So can anybody tell me what a domain of a function is? All the possible.
Is it like negative, negative, positive?
You're on the right track of what it looks like.
It's the x values.
Good, the x values. So it's all the x values of the function. So if that's all the x values, then the range would be all the you got it, y values. So this function on its domain, basically it takes on every value for x except for where can it not exist? Good, yeah, on the asymptote, right? So it goes everywhere except for -2, doesn't it? So how we write that as a domain is it goes from -infinity to -2, and then it stops, right? It stops here. It's going from -infinity to 2, and then it just stops because it can't go any further over here. It stops like the vertical asymptote is like a wall. But then on the other side of the wall, it picks back up, right? And it goes off to positive infinity. So union, other side of -2 to positive infinity, the graph picks back up. So that's why we write it like that. That basically is another way of saying all real numbers except for -2. So it stops at -2, picks back up after -2 is over. It's like here and here, stops, picks back up. So that's how we would write our domain and interval notation for this type of situation. Now we're going to go into range. So range is going to be all the possible y values of the function. So that's going to go from -infinity up to 1, and then it stops and picks back up after 1, which is its horizontal asymptote, to positive infinity, just like that. Now once we've done that, we're going to determine end behavior. So this end behavior is pretty straightforward on this graph. In both directions, my function gets closer and closer to its horizontal asymptote, which is at, what's the horizontal asymptote at? 1. So if you missed anything, here's your zoom out so you can see everything. And that's what this looks like.
So your end behavior is always the horizontal asymptote?
Not always. In this one, you can see that it is because see how these two sides get really close to it?
Yeah.
So when you have a graph that's shaped like this, yes, but we're going to be looking at a lot of funky looking graphs today, so unfortunately no. But you'll see what I mean when we get to the other ones. So does anybody have any other questions about this one? All right, let's look at number 2. All right, so number 2, let me zoom in. First thing we want to do here is we wanted to determine the degree of the numerator and the denominator. So this is the product of two binomials. Can everybody see that? If you were to FOIL out those binomials or use area model, whatever method you use to multiply two binomials, what would the degree on the x be? What would the exponent be?
1.
If we were to multiply this, it would be x times x, which is x to the 2. So the degree of this would actually be 2. If you were to multiply it out, it'd be 2. Now, as for the denominator, what's the degree of the denominator? 1. It's just 1. So in this case, which classification would this one be? The degree on the top is bigger than the degree on the bottom, right? So it's top heavy, right? So this is a top heavy degree. So that's just right from my instructions manual, okay? And the instructions on top heavy says we have no horizontal asymptote, but if the top degree is equal to the bottom degree plus 1, then we may have a slant asymptote. So we don't have a horizontal asymptote because it's top heavy. You're never going to have one when it's top heavy. but you could have what we call a slant asymptote. So before we determine if we have a slant asymptote, we want to graph this first, because if too much stuff cancels out of the graph and it just ends up being a linear function, we're not going to have a slant asymptote. So we want to see if that will happen before we try to do extra work. So I like to determine if I have to do that work first, save myself the work smarter, not harder, right? So we're going to wait on that. Next thing we're going to do is determine, is this fully factored, yes or no? Yeah, it's fully factored already. So this one saved you the time. You don't have to factor anything. If it had not been fully factored, that's where you would have factored it. Okay. So now we're going to talk about the removable restrictions or discontinuity. So looking at this equation, will anything cancel out of it? Yeah, see how the x minus 1 would cancel out? Those are what we call our removable, our removable discontinuities. So how we actually find this is, we take whatever you're removing, and you set that piece equal to 0. So whatever gets removed gets set equal to 0. Now, to figure out the x value for this, we simply are just going to solve for x, and we get x equals 1. Now, a removable discontinuity will always be an ordered pair. So, when we canceled out x minus 1, what are we all ultimately left with as a function here?
Y equals x plus 3.
Exactly, y equals x plus 3. So, to find the y coordinate of the removable discontinuity, what do you think we're going to do? Good, we're going to take our new equation and we're going to plug the x value into it to get the y value, which is 4. So this is our removable discontinuity we just found, 1, 4. So everybody see what I did there? Okay. So now we're going to talk about non-removable. And non-removable discontinuity occurs where we have something left in our denominator after simplifying. After we simplified this function, was there anything left in the denominator? No. Nothing left in denominator. So if there's nothing left in your denominator, you have nothing to worry about as far as non-removable asymptotes, which are ultimately your vertical asymptotes, by the way. The non-removable are also known as the vertical asymptotes. So, now that we have that much information, I'm going to zoom out here, and I'm going to go ahead and graph the point that we just have as our removable or our removable discontinuity. So, how you graph this, zoom in on your graph, where that point is, which is 1, 4, you're going to put an open circle on it. So instead of like a filled in circle, you're going to put an open circle. Mine wasn't that good. It's going to look like this, like a hole. That's how you plot a non-removable a non-removable point, okay? Just like that. Now, we're going to look at the function we have left. And we have to determine the x-intercepts. So, the way that you find the x-intercepts is you take the numerator of your function, and this function happens to only have a numerator, and you're going to set that equal to 0. And if you have multiple factors, you're going to set each one of them equal to 0. And that leaves me with an x-intercept at negative 3, 0. And then to find your y-intercept, you're going to take the entire remaining equation, and you are going to plug in 0 for x. Solve that, you get y equals 3, which is 0, 3. So we found our intercepts. We can now plot these. So my x-intercept is at -3, 0, and my y-intercept is at 0, 3.
Did you plug in 0 for x?
For which one?
The y-intercept?
Yes, you just take your function, the new function, and plug in 0 for x and solve for y. Exactly. So once y'all are good with that, we will move on to the Desmograph. Alright, so Desmograph. What you can do here is, and I recommend this because this means less margin of error basically, is I want you to actually graph the original graph before we cancel anything out. So y equals, and I gotta find it because I don't remember what it was off the top of my head, x plus 3, oops, that's x equals, times x minus 1, all divided by x minus 1. So that's the original graph. And the reason we do this is because it will tell you where your discontinuity is in the table. Now we didn't have any asymptotes or anything, so we didn't have to worry about that. Now, what do you notice about this graph? Does it look familiar to you? Yeah, it's just the most basic function, right? Yeah, it's a linear function with a slope and a y-intercept. Does anybody know why it ended up being linear? Because what happened?
When divided the x minus 1, you took the x minus 1 out, so it's only x plus 3.
Good, yeah, it would cancel it all out, yeah. So the only thing that Desmos won't give you, which is why you had to figure it out, is the point of discontinuity. See how on the graph here, we know that this point doesn't really exist? Now the Desmos will tell you it's undefined when you zoom in, but it's not going to put an open circle on it, you know what I mean? Until you click on it. So just be aware of that. That's something you have to find yourself manually. Now once you have this, you can hit the little gear and then hit convert to a table. And as you can see, it will do the table for you, and at 1 it's going to be undefined. Everybody understand why the 1 is undefined? It doesn't really exist, right? Because we just found the hole in the graph. So let's go ahead and finish graphing this. So this one's simple and easy to graph. It's just a linear function. So it's just, oops. Here and here, and then you can just connect it. To the best of your abilities. And that's somewhat of what your graph will look like. So now that we've done that, we're going to talk about domain and range. So this function will take on every x value except for which x value? 1. So it's going to go from -infinity to 1, union, and then it stops and picks back up after 1. And then, you know, in contrast, it's going to take on every range value except for which one? 4. Okay. So that's what we end up with. And now we are going to determine the end behavior of this graph. So as my graph, as we look at my graph on the left, it's going down. And as we look at my graph on the right, it's going up to positive infinity. So neither of these sides are approaching like a line or an asymptote or anything like that. The asymptotes help us determine end behavior. In this case, there are no asymptotes to help us determine that, meaning it's just going off into infinity in both directions, negative or positive. Now, as for the slant asymptote that we talked about, I want to talk about when you do and don't have to find this, if it's top heavy. So, as you can see, this graph is a slant itself, meaning it's a line. So you don't have to find the slant asymptote because it's a line itself. So you don't have to find it. If you get a linear function, you don't have to do it. Does that make sense to everybody? Alright. Before we move on, would you like a break?
Yes, please.
Alright, we'll take a 7-minute break. So, the question says, we have this equation, and we have to determine its degree. So, if we zoom in here, what's the degree of the numerator here? Good. The degree is 2, the highest exponential power. And what's the degree of the denominator?
2.
Good. And 2 over 2, that means that the degrees are the same. So that means we follow the procedures for same degree. And the procedures for same degree say that the horizontal asymptote is y equals a over b. And a is the coefficient of the numerator term, and b is the coefficient of the denominator coefficient term. So y is equal to 2 divided by what? What's the coefficient of the bottom one? 1. So my horizontal asymptote is y equals 2. Now we're going to move into factoring this. So what do you notice we have to do to factor the numerator? We have to use what method? AC method. So we're going to use AC method to factor the numerator. So you multiply your A and your C value and factor as normal. That would factor into x minus 2 and x plus 1. And then to finish factoring that, what would I do? Divide by 2, the A value. That comes out to be x minus 1 times 2x plus 1. So that's my numerator. So all I did was I just factored the numerator, okay? That's all that happened there. Now we're going to move into the denominator. So we look at my denominator here. What would my denominator factor into? What two binomials here? Good. -4 and +3, right? So all I did right here was I simply just factored the polynomial equation. Everybody with me on that step? Alright. Once it's factored, we can now do number 3, which is discontinuity, the two types of discontinuity. So removable discontinuity is where anything will cancel out. Now in this case, are any of these binomials eligible for cancellation? No, because none of them are the same, so we don't have any holes in the graph. So now we'll talk about non-removable. So non-removable is where we take our denominators and set those equal to 0, and those will give us our vertical asymptotes. So how many factors in the denominator do we have to set equal to 0? Okay, so we're going to solve these. We get x equals 4 and x equals -3, right? So those are my two non-removable vertical asymptotes. Everybody see how I got those? You take the denominator, set it equal to 0. Now we're going to move on to my intercepts. So, to find the intercepts, you take the two, whatever's in the numerator. So we have x minus 1 equal to 0. And 2x plus 1 equal to 0. Set the two numerators, however many products there are in the numerator, set those equal to 0, and solve. This gives me x equals 1, which means I have an x-intercept at 1, 0. And this, if I solve it, would give me x equals -0.5, which means I have another x-intercept at 0.5, comma 0. And then for y-intercepts, to find a y-intercept, you take the entire equation and you replace all of the x's with 0. Okay, you take the entire equation and replace all of the x's with 0. Now you can use the factored or non-factored form. They will give you the same answer. And just for the sake of time and space here, I'm going to do the math for you here because I know you're all capable of that. And that comes out to be y equals 1/12, meaning that the y-intercept is 0, 1/12. So, for domain and range, we're going to have to wait on that because we need to first see the graph. So, let's zoom out and graph everything. So, we have a horizontal asymptote at 2. That's my horizontal asymptote. Bless you. We have 2 vertical asymptotes at 4. Oops. I want to make it in blue so it's a different color. At 4 and at -3. X equals x equals 4 and x equals -3. And then we have some intercepts to plot. I have an intercept at 1, 0, and I have one at -1/2. So to finish this off, I'm going to zoom this in here. And I'm going to graph my y-intercept. So what's 1/12 going to look like when I graph a y-intercept at 1/12? Like, where's that going to fall? Yeah, almost at 0, like just a little above 0, okay? So that one's really tiny. So that's everything that we came up with. So now let's look at our Desmos graph. So are you ready to see a very interesting graph here? Okay. So this is what the graph actually looks like if you were to graph it. And as you can see, we have this shape right here happening, and then we have these 2 on the side. So it bends all around our 3 asymptotes. So if I go to settings table, it gives me a few table values for my graph. I want to pick one that comes out a little nicer than that, so let me try a few different values. Alright, we have a point at 5, 5.5, so go ahead and plot that. 5, 5.5. We have a point here. And then we have a point at -5, 3. And you can start picking up some points on the graph. It looks like we're also going to have a point at, let's see, -2. We have a point at 1.5. So -2 is right here, and then 1.5, 1. It's right about here.
Can you zoom in on that once you're done?
Yeah, I'll zoom in. I know I can actually do that now. That might be easier, right? Here you go. Is that better?
Yeah, thank you.
You're welcome. Yeah, -2, -1.5, right here. And then once you have a few points, you can go ahead and start sketching this. 7.3, we have a point. So your goal is to just pick a few points that will exist on the graph and graph decently nice so that you can kind of see what it looks like. And then you can go ahead and sketch it. So it's going to look like this. And then it goes like this. And then the same thing over here. So that's what your graph's going to look like. So, like I said, sketches are fine. Pick a few points on the table, and then from there you can just sketch it. I'm not looking for a masterpiece here. All right. So now we're going to go ahead and determine our domain of this one. So for this equation, what two values can x not be in this one? We're looking at our non-removables. It can't be. Good. -3 and 4. So my function's going along just fine from -infinity to -3. And then it's got to stop because we have this asymptote right here. And then it picks back up from -3 and it goes until we get to 4. So my function going until we get to 4, and then it stops again. And then it picks back up after this asymptote right here at 4 to positive infinity. That's what your domain is going to look like. And then as for my range is all the possible y values my function takes on. So from below, my function is coming up from -infinity, and then it stops right here at this point, the y-intercept, which is what? What's the y-intercept? 1/12. No, that y-intercept was 1/12. And then from there, and then you're right, this part, it picks up at 2. Picks back up after 2 to positive infinity. Yeah, because it stops here and it doesn't go above that. And then it doesn't pick up back up until after we go above 2. Does that make sense, how we have that space here in the middle? Mm-hmm. Okay. So, does anyone have any questions about this? All right. So, what we'll do on the next two is we'll go through and do all of the math portion of it. And then what I would like to do to finish off here. Oh, interesting. Okay. So we'll do the math portion, and then I'll have you do the graphs yourself, because it's pretty straightforward, and that way, you won't be so bored sitting here watching me. And then you can check it with me. So on this one, the end behavior on both sides is going from -infinity and positive infinity. Wait a second. No, it's not. 2 and 2. Sorry. I don't know why I said that. It's 2 and 2. All right, is everybody ready for the next problem? Okay. All right, so the next one we're going to be looking at is example 4, and we have to determine the degrees, okay? So this one can be a little bit tricky to determine the degree of. So, what happens if you were to distribute here on the top? Good, we would get x to the third. And what would happen on the bottom? Well, we can't do anything, so it's just x to the second. So this one is top heavy. Top heavy. So then, moving on, thank you. Now we're looking at our horizontal asymptote. So this one does not have one. And the reason it doesn't have one is because it's top heavy. But it may have a slant asymptote. So the way we find the slant asymptote is we actually use synthetic division. So what we do here is we have to first factor this, okay? So we're going to factor this first before we do anything else. So let's come back to that section. Let's factor this. So, as you can see, my numerator of my function is already factored, but what about my denominator? What can my denominator factor into? What are some factors of -3 that add up to +2?
Negative 3 and 1, or 3 and -1.
3 and -1, thank you. Goodness, I feel like I'm teaching to like static right now, you guys. Okay, so then from here, let's go ahead and find our discontinuity and whatnot, because we have to do that before we, cancel anything out. So what do you notice about this function that's going to cancel out here?
X plus 3.
Thank you. X plus 3 is going to cancel out. So that's what we call our removables. So we take that and we set that equal to 0. And that gives me x equals 3. And then to find the y coordinate of my removable, I would have to plug it back into the function. Y equals 3 squared over 3 minus 1. And I'm just going to tell you what that comes out to be so that we don't have to spend time doing that math. That's going to come out to be negative 2.25 when you plug it back into the simplified function. Because remember, the function is now y equals x squared over x minus 1. And now our non-removable. So our non-removable is whatever we have left in our denominator after we simplify. So what's left in this denominator now?
X minus 1.
Good. So you're going to take that and you're going to set it equal to 0 to find your vertical asymptote. And that gives me a vertical asymptote of x equals 1. Alright, so now we are going to go back and find our slant asymptote. So sometimes the slant asymptote can help you graph, okay? So the slant asymptote can be found with long division. Because it cancels out, we're only dividing with what's left and then disregarding the remainder. So you'll see what I mean. So do you prefer to use long division or synthetic? Synthetic? Okay, let's do synthetic division. So what we have to do here is we have to divide this into this here. So the denominator into the numerator. So what would I put on the outside here of x minus 1? What's going to be my number out here? You remember this? Positive 1. And now we need the coefficients of x squared, which is
X.
1, and then it would be 0 and 0, right? Because we don't have a x or a constant. Do you guys remember what I'm talking about here? We're doing this division right here. So this, basically it's this divided by this. So let's do the math. We bring down the 1, multiply, combine, multiply, combine. That's our remainder. Now how would we rewrite this? It would be x. It would just be x plus 1, because remember the last one's the remainder. Actually, what we do is we just ignore the remainder in this case. Yeah, so you can just disregard the remainder, and this gives you y equals x plus 1 as your slant asymptote. Okay, so now we're going to move into the intercepts. So to find our x-intercepts, all we have to do here is we have to set our numerators equal to 0. So what factor do we have in our numerator here? What's left in the numerator of this fraction?
X squared.
Good, so you're going to set that equal to 0. And that just means x equals 0 is your x-intercept, which is at 0, 0. And then to find your y-intercept, you take the entire equation and you replace the x's with 0. And that gives me 0 divided by negative 1, which is just 0. So then from here, we are going to graph this. So let's zoom out. Okay, so we're going to graph the removable first at 3 comma negative 2.5-ish. So 3, and then down to right about here. Oh, it was negative 3, not positive 3. That's why. It's over here, down here, here, somewhere around there. Yeah, about there. And then we have a y-intercept right here. And then we have our asymptotes that we just came up with, which are at x equals 1. And then we also have our slant asymptote. So what do you notice is different about the slant asymptote versus any of the other asymptotes? Alright, so we're going to graph our slant asymptote, which is x plus 1. So that's going to be a vertical line starting at here at 1. And it's going to go up from here, so it's going to look something like this. And then what we would do here is we would just graph some points on Desmos, and your graph ends up looking like this. And as you can see, we have our hole in our graph. And then we would determine our domain and range. So in this case, my function takes on every value except for where it touches the vertical asymptote right here. So that's going to go from negative infinity to 1, union 1 to positive infinity. And as for my range values, my function's coming up right here from negative infinity up to 0. And then it stops and doesn't pick back up until up here. So in order to find this point, we'd have to know what that point was. It looks like it's at 4, which you can find on Desmos. So that's going to be from 4 to positive infinity. And my end behavior is going to be from negative infinity to positive infinity.